All right. Yeah. Thanks so much for the intro, Michael. And yeah, happy to be here. And so yeah, I will talk about why Ethereum synchronization sucks and a hint of how to fix it. So I'm a co-founder and CTO of MegaETH, and I'm also graduating from MIT with my PhD in 4 days. All right. Thanks so much. All right, so if you have recently tried to synchronize a GETH client, you might have seen this message and this. So very likely, you'll be stuck in a state called state healing for, let's see, weeks, days, months. I'm not sure if years. I think Ethereum is not that old, but I think the general consensus, or at least from my research, from my search on GitHub issues on Stack Overflow, and even just a sample of 3 in our audience, is that it really takes so long. And let's see why it does so. So what state heal does is it tries to fix inconsistent states. That's what it means by heal, right? So what do I mean? In your GETH client or any Ethereum client, there's a database called the state database that stores the blockchain state, like the account balances, the storage values, etc. And the key takeaway here is that every piece of the information in this database is a small kind of 46 to 86 bytes entry, very small piece of data, but a ton of them. So when this database is inconsistent or corrupted, you need state heal. So when does it become corrupted? Let's see. So the most common case is that when you just start to synchronize a GETH client. So what it does is that the client will try to fetch pieces of information in this database from different sources concurrently. And because blockchain is a moving target, right? The blocks are being produced, at least in the case of Ethereum, every 12 seconds. Different peers that you try to synchronize with might have slightly different desynchronized view of the blockchain. So they are not, so the databases they hold are not fully consistent either. And when you try to download shards of data from them, what you get will also be inconsistent, right? Some of the data will be kind of as of, say, block 1 million. Some of the data will be kind of as of, say, block 1 million plus 1, right? So that's the gist. And then it's inconsistent. You want to kind of fix it so that the entire database corresponds to the state of a single block on the Ethereum blockchain, and then you go from there and basically apply all the subsequent blocks from there, and then you are synced. Another example is when your node decides to crash or to sleep for a while, and while the node sleeps, the Ethereum blockchain is still going, right? So the state keeps changing, and now your state is outdated, and you want to kind of synchronize to the tip of the blockchain. Okay, so currently, state heal is implemented as Merkle tree traversal. So I think most of the audience will know that Ethereum and many blockchains will build state tries or Merkle-Patricia tries over the state database. And each node in this state trie is the hash of its children. So the gist here is that if you compare 2 nodes, 2 internal nodes of the tries, you can basically compare whether the data that are below them are the same across 2 tries. So what we can do, and what currently state healing in GETH is doing, is they are going to compare the 2 tries from the root. So if the root are the same, then their tries are consistent, right? It must be the same. But if not, then they're going to go level by level below to figure out what actual nodes and what actual leaves are differing across their tries. And then by doing this, you kind of figure out what leaves are different and basically what state entries are different. And you can kind of figure out what data you want to request from the other end. So that's how currently state heal is implemented. But the problem here is that Ethereum has grown so big. Each state database has 1.3 billion entries. And the problem here is that doing this hash tree traversal is super inefficient in the sense that first, you are going to hit a lot of random disk IOs. You're going to generate a lot of random disk IOs because the tries are just, the nodes in the tries are just hashes. So they are placed randomly across the disk, and for each node that you want to look up and you want to request from your peer, both you and your peer will have to do a random disk lookup. So it's insanely low throughput compared to nice and consistent sequential reads on your modern disks. And the second is because we have to go this level by level, right? Because without, say, figuring out if the roots are the same, you actually don't know whether you should go one level deeper. So the problem here is that it takes many round trip times of the network. You have to go level by level. And the third is that there's a big amplification of communication, compute, and I/O. What I mean is that you are actually only caring about the leaves, the actual state entries that you want to kind of figure out which ones are different. But by doing that, you're also querying all the internal nodes of the trace. So everything in this process is amplified by a factor of the depth of the trie, right? So that's a third problem. And these three problems becomes more and more serious when the state trie itself is large, say 1.3 billion items. And that's why we saw those rents. So this talk is about how can we how can we get kind of a semi-optimal, near-optimal solution for this state synchronization problem, but also data synchronization, data reconciliation in general. So we start with an abstraction of the state synchronization problem called set reconciliation. So imagine that Alice and Bob, two computers or two Ethereum clients, each holds a set of fixed length items. And these items can be anything, like file system blocks, database keys, etc., or in our case, the entries in the state database. And what they want to do is to compute the symmetric difference of their sets, A and B. And we denote it as A delta B. It's the symmetric difference of A and B. So the symmetric difference of two sets are the items that are exclusive to only one of the sets. In other words, the two items highlighted here in the slide. So the green item is exclusive to A, B doesn't have it, and the gray item is exclusive to B. So they want to figure out what this set is. And because if they figure this out, they can exchange the items in the symmetric difference so that the two sets become the same, right? So let's first think what we can hope for. What's the optimal communication cost that we can try to shoot for in this process? Obviously, there's a simple lower bound, which is the size of a symmetric difference. Because by information theory, this is kind of the information that you are getting from this process. And you cannot really communicate fewer bits than the amount of information that you are getting. So this is a very nice and straightforward lower bound. And our goal is to try to kind of get as close to this lower bound, which is the size of A delta B, as possible. There are a few very straightforward solutions that the industry have been using, the production system have been using. And for example, Alice, the holder of set A, can just set the entire set, which is uninteresting. And here the cost is linear to the size of her set. And so it's clearly inefficient. You can, of course, use more kind of optimized solutions like sending over hashes of the items, not items themselves, or you can try to build Bloom filters of the items and send over the Bloom filters. However, the key here is that however you try here, the cost is linear to Alice set. Because, fun fact, Bloom filter doesn't really asymptotically reduce the cost, reduce the size. It's just a constant factor reduction. Although a significant reduction, asymptotically, you are still sending linear to the number of items in Alice set. And of course, we have the state hue strategy, which is to compare the hash tries that I just talked about. And the problem is that there's an amplification of the depth of the tray, and you have so many round trip times in the network. All right, so there's actually a very promising solution to this problem, and it's to use a data structure called a linear sketch. So a sketch is a summary of a set, and under some conditions, which I will talk about later, you can decode a sketch to get back the items in the original set for which you built the sketch. So a linear sketch also has a very nice property called linearity. And you can so-called add together two sketches say the sketch of A and sketch of B, and the result will happen to be the sketch of their symmetric difference, A delta B. So the way you can use this nice property is that Alice can just send her sketch of her set A to Bob, and Bob will add over these two sketches so that the resulting sketch will be the sketch of their symmetric difference, and then Bob will try to decode the sketch to recover the items in the symmetric difference, right? So far so good, right? So I mentioned that in some conditions you can decode a sketch, and I will quickly explain how it works. A sketch is a collection of symbols, and each symbol is the sum of a few items in the set, right? And imagine that this is the symmetric difference that Bob wants to decode, and this is the corresponding sketch, which is a bunch of symbols, right? So each item of the set is randomly mapped according to some rule or to a few symbols. And for example, here, item A is mapped to symbols 0 and 4, and so on and so forth. So each symbol is the sum of the items that are mapped to it. So for example, here, symbol 0 is the sum of items A and E. So here, when I'm saying sum, I really mean the bitwise XOR operation, not really literally adding up two numbers, right? It's a bitwise operation, but it's basically it's kind of the corresponding operator of adding up two numbers for, I guess, bit strings. All right, so to decode a sketch, we use an algorithm called peeling. And we start with a symbol that is the sum of only one item, and we call such symbols a pure symbol. And for example, symbol 2 here is the sum of item D itself, so we can recover item D. And we can now remove D from the other symbols it is mapped to by kind of subtracting D from these symbols. And now symbol 5 becomes pure, and it allows us to recover item F, and we remove F, and symbol 1 becomes pure, and we can repeat the process until we recover all the items, right? So this is how you decode a sketch. However, I mentioned you can only do this under some conditions, right? So a rule of thumb here is that a sketch is only decodable with high probability if it has twice as many symbols as the items it contains. And it's a kind of a mathematical result, so really it's not about software implementation, correctness, or something. It's really an impossibility result. So this is because the items are mapped randomly, and you might end up with conditions like this that you don't have a pure symbol to start peeling, right? Here, in this case, every symbol has either 0 or more than one item that is mapped to it, so you don't really have a pure symbol to start the peeling process. Or you may end up with this situation that you may run out of pure symbols halfway as you try to do this peeling decoder. So what we see here is that traditional sketches, although they are very promising, they are also inflexible. So there is a design capacity which is about half of the number of symbols that it can be used, that it can kind of reconcile, right? And the capacity here is fixed when the sketch is constructed. And meanwhile, we do not actually know how many items there will be in the symmetric difference. So if it turns out to be too few, then we are wasting the capacity and we're incurring redundant communication. So because you have to send the entire sketch, which are 4 symbols designed for 2 items, to reconcile, in this case, just 1 item. You are wasting the communication. Or if it turns out to be too many, I mean the symmetric difference, if it turns out to be too large, then it's likely that we cannot recover any item from the sketch because of the rule, right? You cannot really recover more items than the capacity allows for, right? So some existing solutions were proposed using online estimation protocols, but it's an extra round-trip time and at least tens of kilobytes in terms of communication. And also the estimates are fuzzy, which creates its own problems. And also we have to guarantee the sketch, we also have to generate the sketches on the fly which will add computation to the critical path of your application. And this is basically a recipe for DDoS. And again, the sketches are kind of one-time use, right? It's tailored for one capacity. So it's tailored for one particular instance of synchronization, because if you synchronize with different peers, the symmetric difference may be of different sizes, and you have to kind of tailor make a sketch for every case. So what would be really nice, and the question that we ask is if we could design a so-called universal sketch. And here, the sketch has infinitely many symbols, so it has infinite capacity. It can be used to synchronize and reconcile an infinitely large symmetric difference. And meanwhile, each prefix of this infinitely long sketch is also a sketch, and has a capacity that is proportional to the length of the prefix, right? And then what it allows for is that Alice can now incrementally generate a longer prefix as she needs until Bob can successfully reconcile. So to visualize this, imagine this reconciliation protocol, right? Our universal sketch for A is an infinitely long sequence of symbols, and same goes for B. And Alice and Bob can generate the symbols in these sequences on demand. And what Alice does is that now she sends her symbols one by one to Bob, and Bob will take the symbols from Alice and kind of adds to its own symbols. And by linearity, the resulting symbols will be the symbols for the symmetric difference A delta B. Right? And Alice keeps sending symbols until Bob gets enough symbols to decode. And this works no matter how large the symmetric difference is, because Alice can just send more symbols as needed if it turns out that Bob cannot decode with, say, just 3 symbols. So what we did is we actually designed such a universal sketch, and we call it rateless invertible Bloom lookup tables, or rateless IBLTs. And it has all the properties that I just mentioned, and it's the first realization of such a universal sketch that has good computation and close to optimal communication cost. So using rateless IBLTs, reconciling D items, say D state entries, takes on average 1.35 to 1.58 D symbols. And here the coefficient 1.35 to 1.58 depends on the actual value of D, but 1.35 and 1.58 are the bounds. And the computation cost is also low, and generating D symbols requires scanning the set log D times. And decoding is also efficient. It takes about D log D computation to decode D symbols. So I'll quickly explain how we designed rateless IBLTs. Our design space is essentially the mapping from the items to the symbols, right? That's kind of the basic structure of a sketch. And for any item, which is an arbitrary bit string, we want to define which symbols it should be mapped to. And then, because we have a definition for each individual symbol, we also know what the sketch looks like for an entire set. So the key constraint here is that we want it to be communication efficient. In other words, we want to make sure the peeling algorithm that I mentioned, which we saw is a very fragile process, can succeed with not too many symbols compared to the number of the items. Because the number of symbols is the cost, and the number of items is kind of your goal, right? That's the amount of information that you're trying to distill from the process. Right? So in particular, we also want to use only a linear number of symbols, because that basically guarantees a constant overhead, which is the number of symbols you need divided by the number of items that you are trying to reconcile. And yeah, then it means that we'll be very close to the theoretical lower bound. So the problem seems very abstracted, and how should we approach it? So we can try to constrain our design space by considering what kind of statistical properties we need so that we can decode with very few symbols. And let's try to consider the probability that a random item is mapped to some index I. And we call this the mapping probability of the I symbol, right? Or we denote it as rho I. So given any function rho I, we can analyze, theoretically, the resulting random graph between the items and the symbols. So I will not dive into the math here, but in our paper, we mathematically prove that rho I must be inversely proportional to I. And what we actually did was to show the converse, right? If rho I turns out to be larger or smaller than 1 over I asymptotically, then the number of symbols m required to decode D items will be superlinear in D. In other words, as the number of items you are trying to reconcile grows bigger and bigger, the efficiency will decrease, which is definitely what we don't want to see. So to give you some intuitions, here's a graph when rho I is 1 over the square root of I. And you can see that the graph is too dense. So each symbol is mapped to too many items, and there are no pure symbols to start the peeling process. And on the other hand, there's a graph when rho I is 1 over I squared. And you can see that the graph is too sparse, and there are many empty symbols that are not mapped by any item. So these symbols are kind of useless, right? They're just zeros. They don't really convey any information. So when rho I is on the order of 1 over I, we get the correct balance. The graph is sparse enough so that we keep getting pure symbols throughout the peeling decoding process, and it's also not too sparse, and there are not too many empty symbols which just waste space. So at this point, you may realize that what I've been showing has been necessary conditions of making rateless IBLTs work, in the sense that rho I cannot be anything other than being inversely proportional in I. But what we didn't show was that such rho I will actually work. So to prove that, we use a tool called density evolution. So it has root in coding theory, and has been exactly the tool that are used to analyze the so-called LDPC codes, which your iPhone, your phones use to communicate over 4G and 5G. So it has very similar structures, and so there's actually a very interesting connection between set reconciliation and basically how your phone communicates over noisy channels like wireless channels. So so we analyze rho I in this format, 1 over 1 plus alpha times I, where alpha is a coefficient, a parameter that we can use. And we applied this tool on rateless IBLTs. And in the end, we surprisingly get a very nice closed form result, which says you need eta times D symbols to decode D items when D goes to infinity. So here, eta is basically the communication overhead, right? It's the number, it's the kind of the ratio between the number of symbols you need and the number of items that you can reconcile. And we show that eta must satisfy this closed form condition. So this formula is a bit abstracted, so I plotted it. On the x-axis is the parameter alpha that you can choose, and on the y-axis is the overhead of the scheme. In other words, to reconcile 1 bit of information, how many bits do you have to send on average when you kind of choose different alphas for this scheme? And in our design, we choose alpha equal to 0.5. It's not optimal in terms of minimizing communication costs, but it's close. And it gives us some interesting benefit when you actually write code, when you actually program this scheme. So our theorem tells that the overhead eta, when the symmetric difference is infinitely large. But for finite differences, we can run simulations, and here's the result. So the x-axis is the number of items in your set difference that you want to reconcile, and the y-axis is the overhead, and we can see that the overhead quickly converged to 1.35, which is predicted by the density evolution analysis. And the theorem also shows the progress of decoding as Bob receives more and more symbols from Alice. And again, we can compare the theory and the simulations, and we can see that they match pretty well. So, okay, so now we know exactly what rho I function we should use for our scheme, which dictates the probability that a random item is mapped to the I symbol. But However, how can we design an actual mapping rule that conform to this probability function? Say that we want to match an item X to the first M symbols in rateless IBRTs, and a straw person solution is to roll a dice for every index I from 0 to M, and for each I, the dice will give us a random number uniformly distributed between 0 and 1, and in practice, the dice can be just a family of hash functions, which I guess we imagine to give random numbers. And if the random number is smaller than rho I, then we make the mapping because it happens with exactly probability rho I, right? But we'll quickly realize that it's very inefficient because we have to roll the dice m times. And on the other hand, we are only expecting to make log m connections. So you are making so many dice rolls just to make so few connections. Instead, we can consider the equivalent problem. So imagine that X is already mapped to the ith symbol. And now we need to find the next index j that X should be mapped to. And in other words, we need to determine the distance between I and j, the two consecutive indexes that X should be mapped to. And we call this random variable delta. So delta is a random variable, and its distribution is determined by the current index X, the current index I, and the mapping probability function rho I. And very surprisingly, and very fortunately, we get a nice closed form approximation of the cumulative mass function of delta. So I will refer you to the paper for the algebra, but the end result is basically says that you can very efficiently sample from the random variable delta. So the inverse of this cumulative mass function is also very simple. So to actually sample a delta, we basically sample a uniformly random number from 0 to 1 and plug it into this inverse of the CMF. And the next index j is basically I plus the delta that you just sampled. And this is very efficient because we skip all the symbols in the middle and arrive exactly at the next index that should be mapped to. So this is basically the design of rateless IBRTs, and I'll refer you to the paper for the full spec. But to use it, Alice can simply stream her symbols to Bob, and after getting enough symbols, Bob will decode and get a delta B. And then Bob acknowledges that he has decoded, and optionally, Bob can send back to Alice the items that Alice is potentially missing from the symmetric difference. So this way of operating is very similar to the so-called digital fountain concept. It's a concept I think raised at the end of the last, at the end of I think 1990s, and so there are some formal connections to be made between reconciliation and coding, as I mentioned, but the name rateless basically comes from this idea. And there are some very nice side effects. First, the symbols are universal in the sense that Alice can reuse the same symbol stream when synchronizing with multiple peers holding different sets. And also the symbols can be incrementally updated. Basically, if Alice inserts or removes an item, she only needs to update on average log m number of symbols. So it's also surprisingly easy to implement. It took me 388 lines of Go without using any third-party library except for the ceiling function and the square root function from the Go standard library. And yeah, it's also probably the most interesting 388 lines of Go code that I've written. And and users to use the library only needs to define how to hash an item and how to kind of compute the XOR of two items. So we did some simulations and compared with other reconciliation schemes, which is uninteresting for this particular occasion. So I will dive into state hill right away. So I mentioned that you want to synchronize two state databases, which each holds a bunch of state entries, right? Fixed length bit strings. So you can use exactly the same scheme. Alice or the peer on the left side simply streams the symbols to the node who is asking for state here, and the right-hand side node will kind of try to decode as it gets more and more symbols, and when it succeeds, it acts to the original copy, and the process completes. This is one round-trip time, and basically very close to the computational and communicational optimality. So we also ran some experiments. We took a machine of 512 gigabytes of RAM, which actually doesn't matter. It doesn't really use too much RAM compared to the number of items that you are kind of reconciling. It uses an Asian CPU. I think by my standard, it's a 2016 model, a server CPU, and it uses a SSD and a FreeBSD 14.0. So that's kind of the setup. And our baseline is GETH. The original code, version 1.13.10, and also the comparison is Rateless IBLTs implemented in our library, and another about 1900 lines of Go code to kind of so that it can read and write the state databases. And the workload that we are using is the live Ethereum states from between these two block heights, which I'll not repeat, and it corresponds to December 31st and January 4th at the beginning of this year. And to run the experiments, we also simulate a 50 millisecond network propagation latency and a 20 megabit per second of bandwidth, just to see how it works when you have kind of realistic, kind of lower end of your home internet. So the high level takeaway is that we basically tried to synchronize states that are of different level of staleness. Here, staleness is measured by the time for which your stale snapshot, your stale state has not been synchronized. So in other words, the access is kind of, imagine that to be the amount of time that your node has been offline, and now you're kind of booting up the node again and tries to synchronize again. And the y-axis, the left y-axis is the amount of time it takes for your outdated node to synchronize, to catch up again, and on the right y-axis is the amount of data it downloads in the process. You can see this very consistent, about 4x reduction in terms of both time and data. And I was focusing on kind of staleness of 20 minutes to 100 hours, and if you are trying to synchronize even smaller differences, say you kind of shut down your node and then boot it back up again, and probably took maybe 5 minutes, the reduction is even higher. It's probably a 10 to 20 times reduction. So there's also a breakdown of what happens when you use Rateless IBLT and Merkle tries. So in our case, again, Rateless IBLT is just one round trip time, right? Alice sends you the stream of symbols, and Bob tells Alice, hey, I got enough symbols, I can decode, please stop. That's it. So one round trip time. You can see that during this round trip time, you fully saturate the network link between Alice and Bob, 20 megabit per second, because Alice can literally pump the data, pump the symbols without really waiting for Bob to kind of tell her anything, right? Until Bob tells her to stop. And on the other hand, for Merkle tries, first, it took almost 11 RTTs for this bandwidth utilization to ramp up. The story here is that the depth of the Merkle tree is 11 layers. So it took you 11 RTTs or 11 round trips to actually go down to the leaves of the tries. In other words, that's exactly the point when you start to figure out what items are differing. And then you are kind of requesting for the items. So you're kind of waiting for 11 RTTs just to figure out, just to kind of go down the tree. And then, even then, you don't fully saturate the bandwidth because it's all random disk IOs. The serving party, Alice, cannot even kind of get the data from the database fast enough. And so I fixed the bandwidth to 20 megabit per second in the previous experiments, but we also tried for different higher and lower bandwidths. So you can see that as you push the bandwidth of the connection to even higher, the reduction is even greater. Because again, when you have a higher bandwidth, latency matters more, because it actually takes relatively fewer seconds to transmit the data compared to kind of waiting for the first bit to arrive, kind of overcoming the speed of light limit, right? So as your bandwidth goes higher, the reduction goes higher. So it's about, I think, 70 times reduction when you're at 100 megabit per second, which is not an insane amount of bandwidth by modern standards. And finally, it's a scheme, so we have to consider its practicality. So we tried basically maintaining and basically keep updating 1 billion symbols. It's good for reconciling 200 days worth of updates in Ethereum. And for Alice to keep maintaining the symbols, it will use 1.6% of one CPU core on her machine, 2016 model CPU, to kind of keep up with the updates in Ethereum. So there's huge headroom if you are building a high performance chain, and also if you just apply this scheme to Ethereum, it's basically giving you a negligible increase in the computational cost. So this work has been accepted to SIGCOMM 2024. So this is actually the first time I'm presenting it to a public audience. So please look forward to the full version, the final version of the paper. And I will repeat two key takeaways. We basically have a scheme for you to synchronize arbitrary data sets that has this very nice ratelessness property, and also is provably efficient communication and computation-wise. Yep, thanks, and thanks for your time.